You're listening to Shortwave from NPR.
Everything you see in this world is made out of matter, from the cells in your body, to the stars in the night sky, to the street you walk on. But matter has an opposite. It's called antimatter. And it almost sounds like something out of a comic book.
You can think of them as like superhero and villain.
Jessica Esquivel is an experimental particle physicist at Fermilab. She says that to understand this ongoing superhero villain story, you have to go all the way back to the Big Bang.
About 13 billion years ago, there should have been equal parts matter and antimatter created.
Jessica says that when a particle of matter and its antiparticle villain counterpart come into contact,
they annihilate in a blaze of glory. And that tiny amount of matter is what we're all made up of.
So if there are equal amounts of matter and antimatter once upon a time, then the mystery is, why didn't they all cancel out and annihilate each other at the beginning of the universe? Because remember, everything you see and touch is made of matter, which means
a minuscule amount of matter survived this huge war.
So why is antimatter basically non-existent? Why do we have a matter-dominated universe now?
So that's one of the biggest questions that we as particle physicists are trying to answer is like, why are we here? Because that shouldn't have been the case with the understanding of physics as we know it right now.
Scientists think that the answer could have something to do with a tiny, mysterious subatomic particle known as a neutrino. Made when atomic nuclei come together like in our sun or break apart like in a supernova. Neutrinos are everywhere. There are billions of neutrinos passing through your fingernail every second. But they're mysterious because they rarely interact with anything.
We like to call them the ghost particles, and they can travel hundreds and hundreds and hundreds of miles without being stopped, and they're very, very difficult to detect.
Today on the show, why scientists are looking to the Hubble neutrino to understand a physics mystery from the beginning of the universe as we know it, and why it involves shooting a particle beam underground from Illinois to South Dakota. I'm Regina Barber, and you're listening to Shortwave, the science podcast from NPR. Jessica says scientists have two potential explanations as to why neutrinos, these particles so tiny their mass hasn't been measured, survived to populate this matter-heavy universe we are in today.
So the first one is that neutrinos are its own antiparticle. So I told you about electrons and their antimatter equivalent, which is a positron. And the biggest change is that their charge changes from negative to positive. Neutrinos, the name means little neutral ones. So they don't have a charge. So one of the big, theories out there is that, well, if they don't have a charge, that means that they could be their own antiparticle. That means you have neutrinos and antineutrinos, which are really just the same thing, just chilling, right? While all this war is happening. And because they have such little mass, because they're so ghostly, it's like not even bothering them. So after everything gets annihilated, they're just hanging out, which means that could be the reason why we have more matter.
So that's explanation one. Neutrinos are neutral, and they are their own antiparticle. Explanation two?
Neutrinos and antineutrinos, which is their antiparticle, they are different, and they oscillate different, meaning they change their flavors as they move through space differently.
That's right. Neutrinos have flavors. 3 known ones to be exact, and they correspond to how they're made. These 3 flavors have scientific names: electron neutrino, and muon neutrino, and tau neutrino. But Jessica likes to call them chocolate, strawberry, and vanilla. As a neutrino and presumably an antineutrino travel through space, they can oscillate between these different flavors spontaneously.
And because they oscillate differently, the neutrinos had an excess of oscillation. Like they created a little bit more strawberry than chocolate matter-wise, while the antineutrinos created a little less chocolate than strawberries. And that could be the reason why we have this matter-antimatter asymmetry.
So in this scenario, both neutrinos and antineutrinos are doing their oscillation dance, but differently. And because of this, that somehow results in more matter neutrinos surviving.
It could be that our universe could express a preference for neutrinos as opposed to antineutrinos. That's possible. And it's one of the things that we're trying to figure out with Dune.
That's Bryan Ramson. He's a particle physicist studying neutrinos, also at Fermilab. And Dune is a massive experiment he and other scientists are working on to help understand this neutrino matter mystery. Dune stands for Deep Underground Neutrino Experiment. Once built, scientists plan to shoot a beam of neutrinos from Fermilab in Batavia, Illinois, to Sanford Underground Research Facility in Lead, South Dakota, 800 miles away.
The FAR detector is a mile underground, and that is to protect it from cosmic radiation and or neutrinos that are coming from the atmosphere.
At its deepest point, the neutrino path is 20 miles underground, and the detector in South Dakota will be massive. 4 units each, about the size of a double-decker jumbo jet. Jessica says it needs to be that big to catch enough of these ghost particles to understand them. And the neutrinos need to travel that far to give them the opportunity to cycle through these different flavors.
Neutrinos change their flavor as a function of how far they've traveled. So you get a lot more oscillation that happens the farther along a neutrino travels. Essentially, we're counting neutrinos and we're seeing how many of them changed. And we have, a mathematical equation which codes in the theory that we think might be right. And if it isn't, if we have an excess of a certain flavor, that points us to potentially there's more than 3 neutrinos. Or, the oscillation between neutrinos and antineutrinos is different.
And maybe those oscillation differences gave matter neutrinos a leg up.
What I would say is that there is some way of producing matter. And in the production of this matter, let's say every 10 billion times you do it, you produce a particle and antiparticle. And then the 10 billion and first time you do it, you produce a particle and an antiparticle, but you produce it in such a way that both of those things together only become matter, and they become a different form of matter than how they were originally produced.
And whatever this process theoretically looks like, it could give rise to a new matter neutrino. And this new matter neutrino has an advantage so that it doesn't annihilate when it comes in contact with an antineutrino.
There are some things where we're very clear on, but the process that I just told you about, that is deeply theory land. We don't know if that exists or not. That's just one way of resolving the paradox. And then there are multiple ways of resolving that paradox.
And Theoryland is where physics explains how an excess of matter neutrinos could lead to all of the matter we see today. The key is understanding that neutrinos are each paired with other forms of matter when they're made. One of 3 particles, electrons, muons, and tau particles. As a group, these 3 particles are known as leptons, and they're some of the smallest building blocks of matter we know of, as in leptons can't be broken down into anything else. So if the universe prefers matter neutrinos, and neutrinos are always paired with another particle when they're made, then this preference might extend to all matter.
Because it shows that our universe prefers at least leptonic matter of a certain type as opposed to anti-leptonic matter. And if it prefers this sort of matter because it prefers a neutrino of this sort of matter, then that connects to the rest of matter in the universe. You basically have to take a detour through Theoryland to understand that. But once you make that detour, there is space for that to happen.
Bryan says that the data collected from the Dune experiment could help scientists determine what's real from that Theoryland. The experiments are set to start in early 2030, once the largest of its kind detector is built.
Is really a tour de force of how we expect to do these sorts of experiments. Like, if you were going to make the perfect detector to do this, Dune is how you would do it.
I think every particle physicist will touch Dune at some point because it's such a big experiment.
one that scientists hope will help answer the mystery as to why matter is dominating our universe. Beyond explaining why all of the matter as we know it exists today, the Dune experiment could provide scientists new ways of looking back in time.
The neutrinos that were created during the Big Bang, they're like a time machine. And we can study those relic neutrinos to see what the situation was during the beginnings of time.
It also might give us new physics that could help us unite theories, from the very large general relativity to the very small quantum mechanics. One thing that could do that, witnessing a proton decaying.
It would be one of the biggest discoveries in physics if we ever actually observed a proton decay. It would mean that some theorist had or has yet to discover how our universe actually behaves.
Dune can also give us new adventures into the unknown.
I think what's most exciting for me is being on the bleeding edge of all of society's knowledge and really scratching at the unknown and then sharing that with folks who look like me and getting them as excited about the unknown, about the quantum realm, about these subatomic particles as I was when I was their age.
The deep underground neutrino experiment is currently under construction and is preparing for the excavation of 800,000 tons of rock at the South Dakota site. This episode was produced by Burley McCoy, edited by our showrunner Rebecca Ramirez, and fact-checked by me, Rachel Carlson, and Burley. The audio engineer was Maggie Luthar. Beth Donovan is our senior director, and Colin Campbell is our senior vice president of podcasting strategy. I'm Regina Barber. Thank you for listening to Shortwave from NPR.